webinar titled Reduce Time to Market with Digital Engineering. Today's guest speakers are Nicola Jovene, Strategic Business Development Manager for Digital Design in the EMEA region at Rockwell Automation, and Paul Christensen, Head of OEM Smart Manufacturing at Project Binder. And now I'll provide some housekeeping information before we start. First of all, I would personally like to welcome you to our webinar platform On24. You will notice that this webinar is browser-based, so if you disconnect for any reason, please just click on the link that you received via email to rejoin the session. During today's event, there will be plenty of time to ask our speakers questions. You can do that via the questions widget on the left-hand side of your screen. Just type your question in the box and click Submit. We will allocate some time at the end of the session to answer questions or any thoughts that you may have. You can also review different types of resources connected to the topic of the event at the bottom of your screen. If you require any assistance, please use the yellow Help widget. In addition, you can move, resize, and maximize any of the windows in front of you to get a better view of the slides. And now, please allow me to welcome Nicola. Over to you.
Thank you. So welcome from my side as well to this webinar session. And in this webinar session, we will see how you can reduce time to market with the digital engineering approach. But let's get started looking at the agenda. So first of all, we're going to see how what are the challenges that you normally face in traditional projects. And then what does it mean really moving to digital with a specific focus on the digital twin technology? And then we'll see the full digital engineering approach and how this can really help you to bring benefits in terms of shorter the time to market. And last but not least, as mentioned, Paul from Project Binder will present real use cases where they use the digital engineering approach and the digital twin technology to reduce time to market. So let's have a look at the traditional projects, as we call. So if we look at the way most of the projects are currently carried out today, it's fully based on what we say waterfall development. So it's a serial process. When one phase completes, the next one begins. So I guess all of you can recognize this workflow, and it's probably describing most of your company project workflow. So it all starts with the early design decision, so concept proposal, then engineering and supply chain, finally with the system design and build and testing, and then on-site work and commissioning, startup and training, and of course operations and maintenance. So I think those are this is a typical sequential workflow. But let's have a closer look at the typical challenges that you can face on each one of those phases. So if you look at the early design decision, so that's when you are building a new machine or a new manufacturing plant, and all the decisions are based normally on estimates or previous experience with other projects. So the performances and the output are normally based on trust and commitments. There is limited proven data. And that's the case when you build a new machine or a full line, and you want to ensure your customer that the machine will produce a certain amount of products per hour or eventually a certain capacity. So the question is how you can guarantee and demonstrate it. So it's all based on historical data trust. There is no way to show and prove it with the real data. Now, once the concept is agreed and the proposal has been accepted by the customer, the end user, now you need to design the system, the mechanical, the electrical automation components, building, assembling, and testing and validating the whole system. So that's where the mechanical department will make the 3D CAD drawings, full mechanical design. So the electrical department will generate the wiring diagrams, the electrical design, and the automation engineers can start deploying the PLC code. But they need to wait for the machine to be built physically before testing the PLC code. And that's normally happening late in the project. So once the machine is already built, and normally you have very limited chances to test new design, make experimentation. And obviously, if you find any problems at this stage, it's going to be very hard and costly to fix. Then we move on site work. So that's when you need to commission and start up the machine. And any delay accumulated in the project will clearly be cascaded on site, right? So any mechanical automation problem that you identify on site, it's full of risk. And obviously will introduce delay on the project, which can also impact the quality of your machine in the full line. And of course, project delays means penalties, lost production, and clearly added risk to the project. Now, once the machine is ready, then you need to train the operator. But training the operator can be done only with the operator accessing the real and physical system, which means that the operator needs to travel on site, being in front of the real machine, and learn how to operate and troubleshoot. Then we move on the last part, right? So once the machine is in production, there might be also cases where you want to upgrade the machine, change the layout for eventually produce a different products, or simply increase the plant capacity. So what do you do now? You change the design, again, based on the estimation. You stop the production, implement the changes, and then back in production. But there is no data to prove the change that you are applying will really provide the desired results. And you stop the production eventually for a long time because it needs to a lot of testing. And of course, the design is pretty much inflexible. So those are typical challenges that you can face in traditional project workflow. And I think most of you can recognize all of that. Now, what does it mean really going to digital and going for a digital engineering approach? So it really means that we are moving from a purely serial workflow to a more optimized approach, which means that you can start, you have a concurrent work streams, and you can start different phases in parallel or earlier in the project. And of course, that's only possible if we establish a single digital environment for design, test, building, and commissioning, enabling also the collaboration and communication between different departments and stakeholders working on the project. And it's clearly important moving from physical hardware testing to simulation and emulation. So in other words, adopting digital twin technology, which is the core element of the digital engineering approach. Well, let's see closer how this is possible through all the different phases. So first of all, with the concept and proposal, you can, in the design phase where you are thinking about a new machine or a new facility, it's really difficult to visualize it, right? So that's where you can sit down with the customer, you can easily build and visualize a digital model. And you can also, by building a digital model, a conceptual design, you can show how the system will operate and will behave. You can also run experiments, performances, and that's where you really get some proven and solid data, and you are not using just historical estimation. The system design is where you combine the mechanical and the electrical and the automation system into a single virtual model. And then you move on the automation design and controls testing, right? So of course, having a digital model of your machine, you can start your controls testing, debugging your PLC code against the digital model while you are still waiting, for example, for the machine to be built or components to be delivered. So you don't need to wait for the machine and the control cabinet to be ready. So that's where you can continuously test your logic against a digital twin, identifying logic or mechanical issues. Now that you have the digital model, you can start training the operator as well on the virtual model, just as he was in front of the real machine. And you can start train the operator into the virtual world in a safe scenario, just to get ready for the machine to be built and ready to be operated. And finally, when you are when the machine or the line is up and running, then of course you have a new digital model, which is live, and you can test or make new upgrades, new configuration, evolving the system and proving also that you can achieve the desired result. So clearly you can see that there are three immediate benefits to this approach. So first of all, it's shorter the time to market by optimizing the different phases and also, and of course, cutting the schedule time. Reduce the engineering cost because of course you can find and fix problem much earlier in the project. And also less cost, which is coming through the use and the adoption of virtualization and digital twins. Now, We all know that embracing such type of approach cannot happen overnight. It will require some organizational changes, new resource, but also a mindset change. But of course, be aware that this is not, let's say, an all or nothing strategy. There is no need actually to replace, for example, the tools or software that you are using. We are not proposing to changing, for example, the mechanical CAD or the electrical CAD software, or forcing you to use Rockwell Automation Controller. Instead, it's really about reusing the existing software, the existing content that you have, and make sure that all those tools can work together into a digital environment to improve the collaboration between all the different stakeholders, the different departments. And of course, you need to analyze your own business, understand where it can work more efficiently, where it can bring value, and where to start from. And of course, Rockwell and the partners are here to help you to understand it. Now, so the core technology enabling the digital engineering approach, as I mentioned, it's about a digital model. It's the digital twin. And let's start with a simple question, right? What is the digital twin and how it can help you? So if you have seen, I think in the last couple of years, you have heard a lot of words: digitalization, digital transformation, Industry 4.0, and digital twin is clearly one of those buzzwords. But if you ask any vendor or any user, anyone has a different meaning or a different explanation for digital twin. For Rockwell Automation, the digital twin is a digital representation of a physical assets or system, but it's not just a 3D visual. It's a dynamic model which is based on the physics of the machine or the system, and it really behaves and responds to operational conditions exactly as it would in the real life, in the real scenario. And when we refer to a digital representation, we are not referring to a clone or a digital replica of the physical assets, but we are referring to a useful model. What does it mean, useful model? It means that the model has to have a level of details and granularity, which is useful for what you are trying to accomplish. So it should be, let's say, just enough close to the real model, and not complex, or let's say having a useless complexity based on what you are trying to achieve. So now that let's say we have seen how the digital twin is enabling the digital engineering approach, and how and what is the digital twin concept, how Rockwell can help you to build a digital twin. So the answer is Emulate3D software, which is a unique software platform enabling you to build such dynamic physics-based digital twin that can be used for different use cases, from the concept and the demonstration all the way to simulation and virtual commissioning. And of course, it's not about creating different models, but it's starting from the same model that you use from the concept and just adding more features and functionalities. Now, let's see how digital engineering can really help you. Let's see all the different details of the different phases. So let's start from the concept and proposal. So with Emulate3D, you can build early concept model. You can animate the model with existing or new equipments to visualize and demonstrate dynamically the conceptual model. And so you can generate impressive videos of the system. You can generate virtual experience and really help dynamically visualize the idea and the concept. In any given organization, I think you have people using different tools, spreadsheet, proposal tools. And now that's where you can have a unique place where everybody can look at the same model, understand how things will move and operate. And you can all agree with me, which is much faster to discuss a new concept machine looking at the 3D video dynamic system rather than reading pages and pages of specification of 2D drawings. And I want to show here just one example of the video. And in this video, you see our Rockwell Automation contactor assembly line in US, which is a real line, which is in production now, where we actually used the full digital engineering approach and Emulate3D to build the digital twin. and of course we used from the conceptual all the way to the virtual commissioning. So now that's the case where we have we now need to build the machine, the manufacturing plant. So the mechanical department would generate the 3D CAD drawings, and those normally are static models. Now in Emulate 3D to build the digital twin, what we can do is either we use our standard library objects that you find in the software, or we can simply import and reuse the content that you have already done, like your 3D CAD drawings. So in Emulate 3D, you can import then any type of CAD, add the design features, add loads. You can start simulating all the possible configuration and design while you're still waiting for the hardware. Of course, by doing so, you can clearly identify any failure or mechanical constraint right at this moment, so you don't have to wait for the machine to be built to actually identify those problems. And of course, if you have a digital model, you can test all the mechanical aspects and feedback, of course, those changes to the mechanical department. Once the model is imported, of course, you can also run several experiments, load up all the full system, identify any bottlenecks, optimizing the capacity of the system, and eventually define what is going to be like the final layout of the machine. Now that we come to the controls testing route, so now the model is now built, the layout is finalized with the optimized performance that's been defined on proven data. It's time to test the PLC code. And that's where you connect the digital model that you have created to the automation system and the PLC. In this example, you see an image. It's still the contactor line. It's the same system where we are using Rockwell PLC, but Emulate 3D is also open to any, can connect to any major brand in the market, Siemens, B&R, Schneider, you name it. For Rockwell, you can use both the physical hardware or also the emulated PLC through our software, which is called the FactoryTalk Logic Seco. So basically, you can have the full system virtually on your desk without any PLC hardware. So both the digital model of the machine or the full line and the emulated controller. By doing so, you can identify logical problems, any collision detection way earlier in the project. So of course, solving those issues at this time on a virtual model will help you to avoid any delay in the project. And basically, you can get in front of the real machine with all the PLC code, which is already debugged and tested and validated with 0 errors. So one thing I want to highlight is that if you have other, for example, software which are running and executing advanced mathematical models, like some of our customers using MATLAB or ANSYS, those can be also connected to Emulate 3D for emulating, for example, physical stress or fluids or thermal dissipation. And that's where that's what we mean by a digital engineering approach. It's about extending the tool's capabilities. So if you have already those software, you can connect to software like Emulate 3D. And what we are doing, we are simply enabling technology to connect into a single environment and exchanging data real time. So it is actually, I want to show again just a short video of the contactor line system, where you can see the Logix PLC, which is online, and we are testing the PLC code emulated with Logix Seco connected to the digital model. So we are clearly testing the real code against the digital model as it was the real machine. So moving to the training part. So of course, now the digital model has been optimized, has been tested. With Emulate 3D, you can also create a virtual reality experience where the operator can work and interact directly with the machine. It is a different example, but it's really a way to show you how you can use the software. So you see here 2 operators. It's actually avatars working into this immersive experience into virtual reality. And so there are 2 persons wearing the HoloLens. They are sitting away each other. So and they are able to interact with the virtual machine, with the virtual HMI, which is the real HMI installed on the machine, and then they are operating really on as it was the real machine, right? So think about, you know, the pandemic period where everybody was working from home. How could have trained the operators without traveling or without being, you know, being at home, right? So it is the answer. By doing so, you can train the operator before the machine is built. And once the machine is ready, the operator know how to troubleshoot and how to interact with it. So you don't have to, you can also save time because you don't have to wait for the machine to be ready and then train the operator. But when the machine is ready, also the operator are ready to operate the machine. And here is another, I want to show you also another video on how this is looking like. So you see that the operators can really interact with the machine, with the panel. And again, they are sitting away each other. So it's also a way to make sure that they can collaborate remotely. And in some cases, it's also used as a maintenance tool when you need to instruct someone on how to operate or to find or solve a specific issue. Then it comes to, we are now at the commission and startup. So of course you have tested all the code now, and it's time to commission and start up the real machine. So a couple of things I want to highlight is that everybody's talking about sustainability, which is a great concept. So having the possibility to virtually test the machine can also reduce the product waste, because if you want to load the machine with different products, you can reduce the number of products and you can reduce the number of physical tests. And of course, you can reduce the waste of products, right? Now, when it comes to commission, because of course you have tested quite a lot of the PLC code, I will say 90% virtually. It's supposed that you're going to spend very limited time on site because clearly you need to focus only on the hardware testing, which is something that you cannot test virtually, right? So the cabling and so on. But of course, you can. The big advantage is that you will reduce the time that you spend on site, and of course all the travel cost and the on-site time, which is always an additional cost for the company. And again, this is just I think one of the last video where you can see the full digital twin model, which has been used for the contactor line, and that's the real machine which has been tested, validated, and is of course now up and running in Milwaukee and is producing the contactors. So finally, we are at the last phase, which is about operation and maintenance. Right now, the system is in production, and you are not forgetting about the digital twin. So the digital model is really a live model. In fact, while the machine is up and running, or the full line, you can still work on the digital model by using also the real HMI, if you like, and you can see how and it can be used as a test bed for upgrades or modification throughout the asset life cycle. So any modification or new configuration can be tested and validated on the digital model before it gets implemented on the real machine. So new experimentation can be done without affecting the full production. And even when those are ready to be implemented, the amount of time required to implement on the real machine will be really minimum, because a lot of the test has been done. So you will not expect eventually any surprise or any error in the PLC code. So this means also minimizing the production downtime. So it allows really to define the design based on the real production and the conditions. And of course, it's something that you can work on because it's a live model, and every time you want to test and to validate any new configuration or any new ideas or increase the capacity or changing any things in the design, it's there to be tested, right? So finally, so what are the real base of this approach, right? So like we have seen, is really about reducing the time to market, which means starting the controls testing earlier in the project schedule before the machine is built. And you all know that we are all experiencing supply chain issues, and this is a big problem that we can kind of compensate, let's say, by testing virtually and not waiting for the machine to be physically ready. High quality machine. So clearly, if you have a virtual model, you can test with a couple of clicks, new configuration, new layout, and you can clearly focus on creating high quality machine with optimized throughput and OEE based on proven solid data, not historical estimation. And finally, this approach by having the digital twin is improving the collaboration and communication between all the different departments and teams and all the stakeholders working on the project. And so with that, actually, the idea was to really introduce the full digital engineering approach, the digital twin technology, how this is enabling the full digital approach, and how this can really reduce the time to market. But now, let's see from Paul how this has been implemented on a real use case. Thanks, Paul. I will hand over to you.
Thank you, Nicola. So thank you very much for having me here, and I will just give you a short introduction on who Project Blind are. We are a partner to Rockwell Automation. We are focused on project management, compliance, and subject matter experts when it comes to implementing technologies into different clients globally. So basically, our aspect is to align the OT and the IT infrastructure and getting the different kind of Industry 4.0, as Nicola said before, enable them into the market. So taking the token from Nicola and speaking about how a digital twin can help clients actually improving the time to market, I will give you an example from a customer that we have been working for. But first, as Nicola has stated before, we see a lot of different kind of business drivers when we work with clients on a digital twin project. As said, we are a system integrator, helping clients using the technology and harvesting the different kind of benefits from a digital twin. So these are a couple of the four major areas we can see a digital twin helps our customers. Going from throughput analyze, as Nicola mentioned, machine prototyping, where you can test and validate your different kind of ideas. And then into the virtual commissioning, which my case will be around virtual commission and how we can improve the time to market. And then finally, as Nicola said, the operator training, how we can do this. So pretty much this aligns also with our expectations and our experience on how we help clients in moving in this direction. One thing I would say is the most important thing is that once you have built a model, and that is basically to all the clients that we are working on, once you have built a model, the same model will go through the complete life cycle of a machine or a production line. So as said before, from the design, when you first start sketching up your design ideas, seeing how things are working together, when you go into manufacturing, assembly the system, you can easily find errors and find mismatches virtually. Then from the commissioning phase and then at the end in the operating phase. So I think it's important here from our side and also with the clients that we work to stress out that one model fits completely life cycle of a line or a machine or a unit. So that's one of the key benefits that we see. And the case that we are working on with this client here is exactly what we experience with this slide I'm showing here, where we can actually support our clients. Because as you can see in the top, we always have a plan where we start the design, we manufacture the machine, we do the commissioning. At the same time, at the commissioning, we start doing our control testings, as Nicolas showed before. And we have a deadline, and then everybody believes that we will go into a support area. But the reality is that things are slipping. Things are actually taking a bit longer time. We will need to go back to do some redesign. We need to go back to do some remanufacturing, and then when it comes to the end, in the commissioning phase and the control testing phase, we see so many times that things are done in the last minute and things are done basically on the back of a truck to get it out into production. With the visual commissioning and the digital twin tool, we actually, in this case, also saw a key benefit that we were able to run this parallel engineering, as we call it, from the very first beginning of the project, where we start doing the PLC, HMI testing, aligning different kind of sensors, aligning the setup of the machine, and then being ready to go onto the plant floor. The customer we helped was Kubica. Kubica, it's a global manufacturing OEM. They are expert in material handling and logistics solution, and are serving various industries globally. But of course, one of the key areas is for the isolation material. This is where they one of the key suppliers for them. As you can see on the left side, there's a couple of pictures of machines that are doing. They also do engineering, prototype engineering, and also support of their company. They have production sites in Poland and in Denmark, where they do the machines. So I will just show you a small video here talking about the machine that we actually ended up in producing for them. So basically here I will start with the end. So the result of what we were able to produce based on the CAD drawings and based on the information that we had from the clients. This project here was a buffer infeed line, and it was meant to be an upgrade and sitting between upstream components coming in and supplying into downstream in terms of these components here. So we saw that in this case here, that in this project here, we had a lot of dependencies on actually what was able to come from the upstream side, having goods coming into the production machine, the buffer inlet, but also coming from the side. As you can see, there was three sides input that were being pushed into this buffer infeed model. At the same time, it was also important at the end of this unit here to read some barcodes from the different batch, but also to do some weighing and see whether the weighing of the goods were correct for discarding or for going through the production in the downstream area here. So this is the result from the project that we did together with the client, and basically where they tested the PLC program and commissioning. So let me take you through the different kind of steps in this project here. So as you see, the objectives when we engaged with the client was that we needed to emulate the buffer inlets, and we wanted to eliminate the programming failures. And in this case here, this is a key area because it's not always that we see the clients have skilled or even experienced programmers or engineers that are taking over projects like this. So here we can see a big benefit in actually eliminating some of these program failures or adjustment. We also wanted to reduce the risk during commissioning and reduce the amount of test material when we are running in the model here. And that fits pretty well into this project model me and Nicola showed you earlier in different, how we can do the parallel commissioning in this case. Yeah. So our approach is that when we engage with a client, we discuss, of course, on all of the commercial agreement, in any NDA that needs to be in scope, aligning expectations and agreeing on the deliveries. Then we start importing the CAD files, or we actually use the standard catalogs that Nicola mentioned also. We see that this platform, Emulate 3D, has a lot of standard catalogs that we can actually use, and that will of course speed up the delivery time here. We receive and assess the PLC and the HMI program, and of course the IO list, so we are sure that we have the correct and the right format to begin modeling these things here. So once we start up the Emulate 3D program, we start adding the kinematics and the physics. And once we have added the kinematic and the physics, then we are connected in the PLC tags to the model, and then we actually start running the model virtually in a virtual environment here. Finally, when we have done these steps of the model, we do an online introduction to our client. It could be either a machine builder or it could be an end user for that sake, but we're doing the online introduction. We do the online training with the clients, and then if there's anything during the phase of the model, then we also do some small adjustment for the clients here. So this is basically our workflow, our project process that we see. So let me take you through the steps one by one. So first, we get an outline on what do we actually need. How do the clients believe that the project and the line should look like? And based on that one, we are able to do some estimation on the time that we are going to spend on this project here, and also the problems that we actually are seeing, or any benefit that we can see here. Then we get the step file, in this case here from SolidWorks. We get the step files from the clients, and then we can import that directly into Emulate 3D, and then start working on that, and then putting all of the different kinematics and the physics on that one. So as you see here, this is kind of the workflow when it comes from a mechanical perspective, having a layout system just to get an overview and being able to see what is the actual amount of energy that we need to put into this project here. Then getting the CAD drawings in a known format, importing it to the model, and this is where we start placing the different photo sensors, weighing cells, in feed, out feed of this model here, and where we can start testing the different kind of functionalities. So once we have worked with the mechanical part of the project, then we start adding the PLC tags. And as you can see here in the bottom of the window, this is actually the PLC editor. This is where we connect with the live PLC tags for the different components in the model on top of the screen. This is a screen view of the tool itself, where we can actually see how we can navigate through the different kind of tools that we have available. So to sum it up, some of the challenges that we saw through this project here from the beginning is that we had a pretty low level of hierarchy in the CAD from the project start. So why do I say that as a challenge? That's because when you want to do emulation and simulation of the mechanical design, it's important that you have a really good hierarchy of the CAD drawings that you get. That means that if the CAD drawings are grouped too much, we are not able to add the different movements and add the different constraints in the model itself. So we needed to work from a rather low hierarchy of the beginning of the CAD files to see how we can actually get the different kind of movements, so we can assess the different collisions and troubles that we would see in running in. We also needed to implement the new PowerFlex 525 drive catalog from Rockwell. The benefit of doing this is that this was just launched, and the benefits what was doing this was that we were actually able to get all of the control tags, all of the different hygiene tags, so to speak, from a drive into the model, and actually simulate also that behavior from a drive. And then another challenge we saw is that we were supposed to have a master-slave relationship between two conveyors, because two conveyors with the incline that I show you, they were connected like a master and slave conveyor, and these are not directly linked in the model. But that was one of the challenges that we overcome in the model on how to actually do this. The result of this project here fits pretty much into the product model as shown below. So Cubica expected to have 3 weeks of commissioning on site, but after 1 week already, the commissioning engineers were sent home because the machine was running as it's supposed to, and they had a successful commissioning. Also, a minimum material used during the running in, since we were actually able to reduce the commissioning time with 2 weeks. Of course, a minimum of these try and errors and adjusting with this running in material is used, and that fits pretty good into the message also that Nicolas said with the sustainability, because lowering the amount of the material that we use when running in, that fits a good that fits the sustainability quite well. And then secondly, the result also is that when we deliver the model, the digital twin model to the client, they can actually just start using the virtual reality to start training and do maintenance of the project here. And that was a huge benefit for our client that they could serve their end user in the end. So that was just a small use case, or a small, what I would say, a small example on where we can see that a digital twin actually reduces time to market for clients and for customers, and also reduces the risk of doing projects like this project here. So thank you. I hand it over to you again, Nicola.
Yes, I think we have some question.
Yeah, thank you very much for the presentation. Just a reminder to the audience, to ask questions, you can send them via the questions widget. Just type them into this box and click submit. Please note that you can still send your questions after the webinar, and they will be answered at a later date. And it looks like we've got several questions already. Okay, our first question is, can a terminal expansion and external loads on a system be simulated in this tool?
Yeah, I can take this one. So I think when we talk about terminal, we are referring to an airport terminal. If that's the case, clearly logistics and airport is one of the the sweet spot for emulated, and we have a lot of projects. Some of them are also public. You can see on YouTube there are several videos, for example, of the Gatwick airports. And that's where Emulate3D has been used for new terminal expansion, and also putting external loads. Yeah, of course, this is one of the benefits of Emulate3D. If you think about it, it's quite impossible to simulate like a full load capacity on a huge system like a baggage handling system in a terminal, and yeah, that's the only way to do it is using simulation. And we have done several projects with Emulate3D, also in collaboration with our partners. I hope I answered the question.
I can add a bit to that also, Nicola, because it's also how do we actually simulate the external loads in the system. What we do is that based on the different loads that we see in various applications, we based on the CAD drawings from the actual load, we utilize the load generator in the system and can basically stress the system with different kind of loads based on the CAD files, because so that's also a key benefit that we can use this in the model.
Okay, thank you. Our next question is it possible to simulate failures? Like what happens when one cable is not connected, or similar situations?
Yeah, okay. So I can take this one as well. So we, of course, I mean, in my presentation, it was an eye-level presentation, right? Of not all the technical details has been covered, but thanks for this question, because in Emulate3D you can also test what we call the electrical wiring diagram or electrical cabinet. So you can really emulate also, for example, push button or a full electrical cabinet, and you can simulate also any failures and how this is impacting the the full logic and the system, and also test that whatever action has been planned from an automation standpoint is actually the right one, right? Not sure if Paul, feel free to jump in if you if you want to add anything, right?
No, I think that you're quite right. We are connecting all of the different kind of sensors to the actual PLC tags, and what we have done in various projects is that we simply just simulate the default in the model to see how the PLC and how the system reacts, and that aligned also with what you're saying, that the capability of actually doing some hardwire testing also. So that's, I fully agree, Nicola.
Yeah, thank you. And our next question is, who evaluated your program? Just a second, I lost the question. Yeah, who evaluated your program? Who makes sure that the results make sense?
Yeah, I can take that, Nicola. I think that was during my presentation with the case story. So when our client was programming the system and doing the project, they of course run it through a functional design specification, and they're doing some kind of test protocols and procedures. So what they do when they test the PLC program, they always test against the functional design specification or any test protocol that is made for this kind of projects here. So it's similar as you would do when you are on site with the real products. It's the same test that you do with the digital twin and the system where you test it against the functional design specification that is made out.
Okay, thank you. Right, our next question is, right, can you produce a PLC program with this tool, or at least make changes to existing PLC?
Yeah, so I will take that one first. So can you produce a PLC program? That's the first part of the question. So clearly, I mean, the Emulator is an open platform, so you can do a lot of scripting. So if you have experience with C# or Java, for sure, it's a good way to produce scripting and some specific action. So we have customers producing, starting from the digital model and producing the PLC program from some of the controllers in the market. So clearly this is one of the possibility. In some cases it might be like an out-of-the-box functionality, but if you have some experience, you can quickly do that. And yeah, it changes the existing PLC. I think not sure I understand this one, but for sure, for example, if we talk about virtual commissioning, one of the use case where Emulate 3D is used is when you, for example, you want to migrate a PLC code from older platform to the new one, and then of course you can test and do the migration of the code, test the code before it gets implemented on the real system.
As an add-on, Nicola, you can see with the ICT framework that you have that is produced. This is actually produced in a way that you can export the PLC code specifically to the ICT framework available. So I totally agree with you. The possibilities of having the digital twin creating PLC program is available. But also we need to again remind ourselves what you said in the beginning, that a digital twin is a virtual replica of a physical asset, and this is where you want to use the digital twin to test the machine behavior.
Yeah, thank you. And our next question is, how much time did it take to create the model from first receiving the material to delivery of the model?
Oh, that's an interesting one. So as I said in the beginning of or at the end actually of the presentation, where we sum up the different challenges we had some challenges in getting the right hierarchy of the CADs that we were working on here. And that of course increased a bit to the overall time consuming of doing this. But from starting the project, from the first beginning of negotiation and then to the end of the training and handover, We spend around 50, 55 hours from our side to do this project here with the constraints and the difficulties that we saw. If we have used the standard components from the catalog and these functionalities, we would have been able to do a project like this a bit faster, I would say.
Okay, thank you. And our next question is, how can VR be used for operator training?
Should I take that also, Nicola? Yeah. So the VR is a standard functionality within the Emulate 3D. So once you have created the model, either it's in a layout where you want to assess the layout of a model, or if you've created the machine itself, there simply is possibilities to basically just hit a button for VR experience, put the glasses on, and then you are already in the VR environment of the machine. You can walk around it, and you can assess different kind of situations. We see that a lot of VR experiences when we work with models is for HSE. Evaluation is, do we have the right fit for personal interaction with the machine, and we also see it as a part of the layout verification, that we can see is the layout of the plant of the system, is that does that make sense? So I would say that Emulate 3D is prepared for VR natively in the software.
Okay, thank you very much. And just a reminder that you can still send any questions while watching on demand, and all questions will be answered at a later date. I would like to thank Nicola and Paul for this presentation, and Rockwell Automation for sponsoring this session. To the attendees, you will receive an email telling you how you can access the on-demand version of this webinar, or you can access this through our website, which is pmi-live.com. We look forward to sharing further webinars with you, so please do keep an eye on the website just mentioned. Thank you once again, and I hope you all have a nice day.
Thank you.
Thank you.